Morning and welcome to the Centro Pi seminar. Today we are very pleased to have Vyacheslav Borovitsky as our speaker. Vyacheslav obtained his PhD from the St. Petersburg department of the Steklov Mathematical Institute in 2022. His field of specialization is harmonic analysis, and he's a researcher interested in mathematics for machine learning, especially in challenging applications in the sciences and engineering. During his PhD, he is also associated with the Chebyshev Laboratory at St. Petersburg State University that many of us have heard about through Sergei Tihomirov. And Vyacheslav interests include Gaussian processes, Bayesian methods, probability statistics, geostatistics, and several other topics. So without further ado, please, Slava.
Thank you, Roberto. Thank you very much for inviting me, for introducing me. Thank you, everybody who has come to listen. So, first of all, you can call me Slava. It's shorter and easier. And I will start my talk on what I called on a common ground between geological modeling and machine learning. So this topic is actually the story of one of my papers, which was the product of ideas from two different fields, from geological modeling and from machine learning. These two fields studied the same tool, and they wanted different things from this tool. And they developed these things for themselves very well. But it turned out that there was some very tiny, very simple bridge between these ideas that actually enables you to get the best of the tools from two perspectives. And this is what I will talk about. And I will start with geological motivation, probabilistic learning for geological modeling. Let's consider what it is. So consider this problem. You want to model a geology deep underground, and your data is just measurements from some very sparsely located wells. So it may look like this. You want to model the volume between two different color surfaces, and the wells are these vertical lines passing through these surfaces. Now, the solution may look like this, but the most important idea that I want to convey here is that in a setting like this, one solution is not enough. Because these wells are located very sparsely, you should either have some prediction and some measure of uncertainty associated to this prediction, or you have to have the whole ensemble of these solutions, which will be equally plausible given the sparse data. And generating these ensembles of different solutions, different interpolations, is something that is quite often done in geological modeling. Okay, now the tool which is used in geological modeling to solve this problem is usually the Gaussian processes. So Gaussian processes are random functions such that for any finite number of inputs, the corresponding vector of outputs is multivariate Gaussian. The distribution of a Gaussian process is characterized by two deterministic functions, by a mean function and by a kernel or a covariance function. And the fact that this distribution can be so simply characterized is what it makes Gaussian processes so attractive to use in the applications. Because of this, people use this notation that I will use further in these slides. So when we have a Gaussian process distribution with a particular mean function and covariance function, I will write it as this. Okay. So on basis of these kind of stochastic processes, there is the actual tool, which is what makes interpolation possible, which is called Gaussian process regression. Now, it's a regression method that takes as its input some prior Gaussian process. That is a Gaussian process that you get somehow from the top of your head. You have to think of this as encompassing some of the structure of the problem that you know of a priori. And in practice, there are just several ones that people just use. And it takes some data. And then it returns another Gaussian process in the form of two updated functions, m tilde and k tilde. And these functions can actually be explicitly expressed in terms of functions m and k of the prior Gaussian process and of the data. The functions m tilde and k tilde are called the posterior mean and covariance functions, or the conditional mean and covariance functions. I will not tell you how to express m tilde and k tilde right now, but I will show you how intuitively this Gaussian process regression works. So Gaussian process is a distribution over functions. So we can visualize it as an ensemble of its samples. Here I took a prior Gaussian process and drew a lot of its samples with different colors. I can draw much more of these samples and get a picture like this. And then assume that we observe some kind of data visualized by these three black points. Now, what the posterior Gaussian process is intuitively like is that it's the ensemble of these samples from the prior which pass close to the observed data. So if we get rid of all the samples which do not satisfy this assumption, we get something like this. And these are basically samples from the posterior Gaussian process. In one dimension like this, for modeling one-dimensional functions, people visualize Gaussian processes in this way. They draw this bold blue line here. And this is the prediction, and this is the function m tilde, basically. Now, the shaded blue regions represent uncertainty. The wider this region is, the higher is uncertainty, and the height of this shaded region at a particular point x is proportional to the function k tilde of xx. So it's just proportional to posterior variance. Okay. So this is the intuition behind this tool. And in geological modeling, for example, what people would do is to take data coming from these wells and consider a posterior Gaussian process and samples from this posterior Gaussian process as an ensemble of answers to this problem of interpolating this sparse data. Okay, so this is one application, and so I presented one application, the geological one, and the tool which is used to kind of solve the problem in this part of the story. And now I want to present another application. It's application to optimization, and it's usually studied within the machine learning community. community for historical reasons, basically. So let's consider the problem of minimizing some unknown function phi in as few evaluations as possible. The motivation is basically that this is a very hard to evaluate function. For example, it may be a function which requires several days of computations on a whole cluster of machines. So you don't want to spend this kind of computations not rationally. Also, people usually assume in this case that this is a black box function. So you don't know much about this function. You cannot differentiate this function, for example, although you usually assume that it is smooth. So you have this very hard to evaluate and thus hard to optimize function. And Bayesian optimization is a technique that allows you to optimize it rather well within some fixed budget of evaluations. It works like this. So you build, again, a Gaussian process posterior, which I denoted here like this, using some prior Gaussian process and using all the prior evaluations of this unknown function as data. Then you use this as a proxy model to help you acquire the next x, to help you choose the next point at which you should evaluate your function phi. And you do this in a following way. You do this by maximizing something that is called acquisition function, and which is determined by your proxy model, which is a Gaussian process. One very natural example of this acquisition function is expected improvement, for example. So it looks like this. Here you have basically the current minima of the function phi that you have on the basis of evaluation done so far. And here you have your proxy model, which is a Gaussian process. Here it's the posterior Gaussian process, and it's a random variable. So now this maximum is a random variable which tells you that if you would imagine that instead of the unknown function phi, you would have probabilistic approximation f, and you would want to minimize it, what would be the improvement over the current minimum? And then you take expectation of this improvement, and this is a deterministic function, the acquisition function called expected improvement. So in order to choose next point, you basically choose the x at which you have the maximal value of this expected improvement, which is very, very natural. It turns out in the end that in order to solve one optimization problem, you solve a bunch of optimization problems. So at each iteration, you optimize acquisition function. But acquisition function can be, in most of the cases, it has some closed form formula. It is differentiable, and it's a good function. So it's quick to solve this optimization problem. And it's not so for the original unknown function phi. So again, I will show you how it looks like visually. So here we have just one iteration of this Bayesian optimization for a simple function. What we see here is this part. This is a Gaussian process visualized as before. And the red line is the acquisition function. Now the dashed line is the location of the maximum of this acquisition function. And here, this point is basically the thing that we evaluated, the outcome of evaluation phi at this point. So In this first iteration, we maximized our acquisition function and evaluated our unknown function here. And now we update our model. So we built new posterior Gaussian process, and it looks differently. And the acquisition function looks differently. And it suggests to evaluate it at another point. And it goes like this. The interesting thing is that this procedure manages to trade off uncertainty and the prediction given by our model. So at some iterations, it will go for kind of destroying this bubble of uncertainty, while in some other iterations, it will go around the area where we acquired the most promising results so far, and will go to make these results more precise. So here, after a few iterations, we have more or less converged. One application of this Bayesian optimization in kind of real-world problems that I like to show is this paper, Basin Optimization in AlphaGo, by people from DeepMind, where they explain how they used this optimization technique to tune the parameters of different parts of the AlphaGo software to get the final version that was actually able to overcome a professional human in the game of Go. Okay, so this is this more or less ends the first part. So let me recap that there is this geological problem of interpolating sparse data and getting samples and an ensemble of these plausible solutions, right? And people use Gaussian processes to solve this problem. There is another problem in optimization, and this problem is one of the solutions to it is Bayesian optimization, which is studied for some reason by the machine learning community. And here it's also the case that they use Gaussian processes as a tool to solve this problem. Okay, now I want to talk about efficient algorithms associated to these Gaussian processes. And this will be the actual story about these different communities wanting different things out of these algorithms and bridging these different things to get more. Now, before we go into efficient algorithms, let me answer the question, which algorithms do we actually need to work with Gaussian processes? The first thing that we want to do is to condition Gaussian process, that is, to get the posterior Gaussian process out of the prior. So this is something that gets us pictures like this. And another thing, which is in a way harder, is sampling from Gaussian processes. So after we have the mean and covariance function of the posterior Gaussian process, get the an ensemble of sample paths of this process. And this is another thing that we would like to do with Gaussian processes. So as it turns out, sampling is often more important to the geological part of the story, because they basically want to get their solutions in many cases as ensembles of samples. And conditioning is something that makes it possible to evaluate the acquisition functions in Bayesian optimization, the simple ones at least, in closed form. And so this is something that is more that is studied more in the machine learning community. Okay, so And why do we need efficient algorithms? Well, the problem is that conditioning costs us n cubed, where n is the number of data points, and the conditioning and then sampling, well, doing this in a straightforward way, costs us n cubed plus s cubed, where n is the same and s is the number of sampling nodes. Okay, so the idea of efficient algorithms would be to reduce the cubic cost of doing this, doing conditioning and sampling. I will start with conditioning. And as I mentioned, this is a part of the story that was studied more by the machine learning community. One reason why it's also not so prominent in geological communities that usually they actually have not a lot of data or approaches that work on grids that allow reducing to neighborhoods and ignoring global correlations, which actually solve these cubic complexity problems. But if you're in a dimension which is a little bit higher, dimension 6, for example, and if you have maybe sparse data, but still a lot of this data, you have a problem with this cubic complexity. And this is a problem that is often encountered in Bayesian optimization. So assume as before that we have data like this, and that we have the standard Bayesian model. So this is basically a more formal statement of the way how posterior relates to the prior. So we assume that our outputs, yi, are obtained by adding some independent noise, epsilon I, to a Gaussian process with the zero mean function and some covariance function k. So this is a some prior Gaussian process, and the posterior Gaussian process is something conditioned on observations like this. Then this posterior Gaussian process is what is used for predictions. So it's another Gaussian process with function m tilde and k tilde as its mean and covariance. And now I'm going to show you how they can be explicitly calculated in terms of functions m and k. So we have these formulas, and I don't expect you to get every detail of these formulas. What I want you to get is the idea that here we have a matrix of size n by n, and in order to compute both of these objects, we need to solve linear systems with this matrix of size n by n. And this is where the cubic complexity comes from. So here I use the notation that if I have a bold letter, then it is a vector of non-bold letters. And if a function is applied to these bold letters, then it's just applied element-wise. So for example, this thing is a matrix of these things. Okay. So now we see where the cubic complexity comes from. And we know what is actually the problem that we need to solve. The idea that is used to solve this problem, one of the most popular ideas, I'd say like this, is to approximate the posterior Gaussian process with a simple Gaussian process, which belongs to some parametric family, with mean function and covariance functions parameterized by some parameter theta. So basically, it's a very popular way in machine learning. You have something and something that you cannot actually compute, you solve, and you think of some optimization problem that you will be solving in order to get some approximation. So the approximation that people use looks like this. You take some vector z of locations, which you call pseudo-locations. And it's a vector of size m with m much less than m. And then you consider a vector, a random vector of pseudo-observations, u, which is parameterized by some mean vector and covariance matrix sigma. Then you put theta equal to this z, mu, and sigma. So this will be the parameters that you will be looking for. And you define your approximating Gaussian process to be the posterior Gaussian process under another Bayesian model, where instead of data x, y, you have pseudo data z, u. And u is noiseless, but u is random now. So the idea here is that we could also consider u being noisy but non-random or something, but this is the optimization family that is probably used most often, and the reason is that it is probably the most expressive one. Yeah, so it looks like this. You kind of change a lot of your data into a smaller number of smaller amount of pseudo data, and you look for the appropriate pseudo data to approximate your exact process. Okay, so now you have to, after getting an approximating family, let me tell you how we can work with the approximation and why it's more efficient. So we have explicit formulas. We can compute explicit formulas for the functions m theta and k theta, and they will look like this. And again, I don't want you to understand all the details of these formulas, but the key thing here is that now, and this is very natural since the size of pseudo data is only m, we have to work with matrices of size m by m instead of n by m. It also requires doing some linear system solving, but now it costs only m cubed, at least if we are given the optimal values of z, mu, and sigma. Now, the optimization problem that we solve to find this is optimizing the Kullback-Leibler divergence. So we minimize this between the approximating process and the true posterior process. And it turns out that you can prove that, first of all, this Kullback-Leibler divergence between two processes reduces to Kullback-Leibler divergence between these two vectors. So you only need to restrict to a finite number of locations here and here. And now, after this, you can actually more or less explicitly compute this Kullback-Leibler divergence in the form of this divergence between two Gaussian vectors of size m, and this part, which is possibly a very large sum of expectations of densities. But the good thing is that this large sum can be subsampled, so you can only take batches of your data. And in order to optimize this right-hand side, you can use stochastic gradient descent by subsampling the sum and by evaluating this expectation by, again, sampling and averaging. And with this said, optimizing this Kullback-Leibler divergence can be also done in the complexity m cubed for one iteration. And we hope at least that the number of iterations will be rather small, so we consider it to be a constant. So the result is that if we have the problem of getting a posterior Gaussian process, and we want to do this efficiently, but maybe approximately, then we can do this by finding an approximation from some parametric family of Gaussian processes which are simpler. And this process turns out the complexity of n cubed into complexity of m cubed, where m is user-defined and it controls accuracy. This is more or less the result of the paper of James Hansman from 2013. And but it kind of finishes the whole line of developments of what is called variational approximations to posterior Gaussian processes. Okay, so what about sampling? Now, there is a very simple way of sampling, and it goes like this. We can take some Gaussian process, no matter if it's prior Gaussian process or posterior Gaussian process, it may have arbitrary mean and covariance functions. And we take a finite set of locations at which we want to sample this process. So some grid discretization of the input space. Then if we restrict the Gaussian process f to this v, we get the random vector f of v, which will have some explicit mean vector and some explicit covariance matrix. Then to sample from this vector, we can just use the representation of it in the form of its mean plus the square root of covariance matrix times the standard Gaussian random variables vector. And to sample from the left-hand side, we can sample a bunch of standard normal random variables and then multiply this vector by this matrix, add this vector, and we will get our sample. And sampling from standard normal random variables is very simple. The problem here is that we need to compute the square root of the covariance matrix, and it takes us again cubic complexity. And also with this method, the sample will necessarily lie on some grid, on some discretization of the input space. We cannot treat it as a continuous function, for example. How can we improve over this cubic complexity and living on a grid? This is a problem that was studied at some place in statistical literature, and most important tool here is based on the fact that priors are usually assumed stationary. This basically means that if you translate your prior Gaussian process, then the distribution will not change. It is invariant under all translations. And in this case, Bochner's theorem gives you a representation of covariance function as inverse Fourier transform of the spectral density. Not in the it's not it can be a general measure in the general case, but we will just assume that it has density. And when we have this part, we can approximate this covariance function by discretizing this Fourier transform integral. So we can sample from this spectral density and think of this as an expectation of random variable of this form, which has density proportional to this. And then we get this average as the approximation. And with this averages approximation of the covariance function, we also get an approximation of the random process itself. The random process itself will look like this. And here it's basically the same exponential function, only instead of a minus b, you have just a, and you have this standard Gaussian weights. You can just check by direct computations that this thing, the covariance of this thing, is actually this thing. And in order to sample from this approximate Gaussian process, you can also just sample a bunch of standard normal random variables, and from this spectral density, and get this. Now, it has linear cost with respect to the size of the grid, if you want to have a grid, because this doesn't require you to have a grid. You get your sample as a linear combination of some closed form functions, and so you can treat it as a function defined over the whole space, which you can, for example, differentiate over this whole space. And if you need, I don't know, optimization over this, you can do this very easily. But this is all for the prior, which has the special structure of being stationary. Posteriors lose this structure. They are not stationary anymore, but there is this trick devised by French mathematician and geostatistician Georges Matron, which goes like this. It says that the posterior Gaussian process can be expressed by this formula. So the posterior Gaussian process on the left-hand side is the prior Gaussian process plus some update term. Here we have a deterministic matrix. Here we have y, it's our vector of outputs of observations. And here is just the prior Gaussian process restricted to the input locations and some noise. So this says that if we have a sample from a prior Gaussian process, we can just plug it into the right-hand side of this and get the sample from the left-hand side. So this is a kind of a transport map between this distribution. So you can plug in some random variable of the first distribution and get the random variable of the second distribution. And we know how to sample well from the prior. So we can sample from posterior by plugging these samples into the right-hand side, doing the necessary computations, and obtaining the resulting posterior sample in this complexity. So it is reduced to linear in the number of grid locations. And again, you don't need a grid, but it's still cubic in the number of data points. So the question is, can we improve over this cubic scaling in this case? And this is the place where I come to this tiny bridge of which I mentioned. So we have a way to sample from posterior Gaussian processes, but it doesn't work if you have a lot of data. And we have a way to approximating posterior Gaussian processes, but it doesn't lend itself for sampling because these m theta and k theta functions doesn't look anything like the posterior mean and covariance functions. So they're different, and this is why you cannot just use Matron's rule to sample from them. So if you would want to use both at the same time, there seems to be a problem. But actually, there is no problem at all, because you can go back to the definition of this approximating family as a kind of hierarchical Bayesian model, where you have random data U, which is used to condition a Gaussian process. And if you think about this in the right way, you get the following simple proposition: that in order to sample from the approximating process f theta, you can just sample the pseudo data u with the mean and covariance matrices found by means of optimization. And then you just need to return a sample from the posterior Gaussian process conditioned on ZU as data. This will be exactly what you're looking for. You can show that this is indeed an approximation which converges to the real posterior Gaussian process, and it turns cubic complexity in both n and s into cubic complexity in m, which is user-defined, and linear complexity in the number of grid nodes. So, yeah, as I said. So this is basically the main idea of the paper, which I mentioned at the very beginning, the paper from 2 years ago of me and my collaborators. And it turns out to be very useful because of the very simple way in which you implement this, and because you can actually solve a lot of new problems that were unavailable due to kind of restrictions that each of the area had. So this completes the main part, but I always wanted, I couldn't restrict myself to just not to talk for 5 minutes about the things that I do right now. So this was the story from 2 years ago. Now my main topic of interest is Gaussian processes on non-Euclidean domains, and this will be very quick, so don't be afraid. By this I mean defining, by Gaussian processes on non-Euclidean domains, I mean defining and using Gaussian processes on spaces like manifolds and graphs. And there is a lot of interesting questions regarding to computations in this case. And to the right notions, to the right prior Gaussian processes that you should use, and to the right algorithms. And this is what I've been doing. So one of the things that motivate this study, that I just want to show you to kind of prove that this might be interesting, is another application of Gaussian processes. And this application is to model dynamical systems with uncertainty. So, of course, if you know the dynamics, you can just iterate these dynamics and get like the state of your system in a few iterations. But it's often the case that you actually don't know the dynamics, but observe trajectories of some unknown dynamical systems. So and you want to learn this dynamical system. So, for example, here you have this pendulum dynamical system, which, if you discretize it, will look like some initial state, then some state x1 obtained by applying this function f to the state x0, and so on and so forth. So if you don't know this f, what you can do is to place a Gaussian process as a model to actually uncover this function f. And what it gives you is that this model will be probabilistic, and this brings all kinds of benefits, like being uncertainty aware in decision-making scenarios. So if you're, for example, learning a robot, it's better if it knows that the prediction for this kind of state, it exists, but it's garbage, because there is very high uncertainty. So modeling dynamical systems like this is something very useful for applications of this kind, for example, reinforcement learning applications. And people actually use Gaussian processes in this scenario. But what's the geometry has to do with this? So even in this very simple case of this pendulum, the state space of the Gaussian process, the state space of the dynamical system is actually an infinite cylinder, so it's a manifold. And it's much better to use this structure, not to just embed everything in a Euclidean space, to model this unknown dynamical system. And many physical systems are actually live on manifolds, and this motivates the study of methods like this. So this is something that we were doing again 2 years ago, but this is a stretching project which I'm doing up to this point. So Gaussian processes on Riemannian manifolds. With this, you can also do pretty pictures like this, for example, modeling wind speeds on the surface of Earth. And there is another interesting question of how you can work with Gaussian vector fields arising from these kind of problems. Also for problems with dynamical systems as well, because in many cases you need to model vector fields to model dynamics. This is from another paper, a recent one from December of the last year. And the very last thing is that you can also do solve all kinds of problems which require uncertainty on graphs. So, for example, problems related to traffic modeling. And here, Gaussian process modeling, which respects the structure of the underlying graph, is something that is very natural and very useful. So this is basically the overview of this another topic that I do, this non-Euclidean Gaussian processes. And with this, I will finish my talk. Thank you very much for listening. And if you're interested in any of these, please feel free to write me or ask your questions right away, right now. Thank you.
Well, thank you very much, Slava, for the very nice talk. I have a couple of questions, but maybe other participants want to ask their own questions first.
Okay, so I'll start. So Slava, thank you so much for the presentation. This was great. So in terms of using non-Euclidean domains, what are the main challenges, in going from Euclidean domains to non-Euclidean domains in terms of the results you've been finding?
Mm-hmm. So the very simple example of such a challenge is that you want to go from Euclidean spaces to manifolds, and you need to come up with some prior Gaussian processes. So the first thing you do is to take the Euclidean priors. You notice that they all depend on Euclidean distance, and you change this Euclidean distance into geodesic distance on a manifold. And then it turns out that this is not a positive definite function, and this doesn't constitute a well-defined Gaussian process. So there is, you either work with this kind of not well-defined Gaussian processes in an engineering way or in a complicated mathematical ways, or you have to develop the whole other perspective on these processes. And this is actually what we've been doing. So it's the perspective through stochastic partial differential equations and through kind of relations to heat kernel and objects like this. So there you have well-defined Gaussian processes, and you don't have problems like this. But then the interesting challenges are computing the values necessary to using these kernels and the problems like this.
So is it computationally more challenging as well?
So for example, consider consider the problem of doing, again, Gaussian process regression on manifold. Consider that you went for the second path and you want to define your kernels in terms of SPDs or heat kernels or something like this. Then you need to know the spectrum of Laplace-Beltrami operator of the manifold. And this is a very interesting computational question on its own. You may fail to actually recover this spectrum in any numerical, in any computationally tractable way. But you can, for example, think of tricks that allow you to not compute all of the spectrum or compute other quantities which kind of work instead of this spectrum. So there is a number of tricks, which is something very interesting and which is actually a very recent piece of work, still unpublished, but hopefully the preprint will be out there in a month. So, for example, devoted to computing or avoiding computing some of the geometric analytical tools, objects required to use these processes.
Okay, I'll keep an eye out on the preprint. Thank you so much.
Thank you.
Any more questions for the audience? So I have, as I said, a couple of questions. I mean, in one of the last few slides that you showed, you had this traffic application. So there, the structure is not of a manifold, right? So it wasn't clear exactly what kind of structure is behind this.
It's a weighted and directed graph, and the problem is the same. So, for example, you may try to go the same path of spotting that kernels for priors depend on Euclidean distance and change it into the distance between nodes of graph, and again get a non-positive definite covariance kernel. And this will be a problem like of using these Gaussian processes. Or you can take another more well-founded perspective from this and get some very natural Gaussian process priors that live on the graphs.
Right. So maybe that suggests another question, which is there any general sense in which, I mean, apparently there are two classes of non-Euclidean spaces, manifolds and graphs, for which you can come up with the right kernels in some sense, right? The right priors. Is there anything that would generalize these two classes? I mean, then any class of spaces where, I mean, if you have this sufficient structure, then you can define the kind of prior that you're interested in the computations.
Yeah, this is a very good question. So the answer is maybe it depends on how canonical priors do you want to have. Like if you want to have a larger class of canonical priors, then, for example, you may take the perspective of homogeneous spaces, right? And in these homogeneous spaces, there will be a group of symmetries which will define stationarity. So stationary Gaussian processes will be the ones which will be invariant under this direction of this group. And you can study these Gaussian processes and you can actually describe all of them. It was done 50 years ago by Jaglom, but there will be a bunch of computational questions, which is very interesting and unsolved, and which we're trying to at least partially solve right now. So this gives you kind of the class of stationary Gaussian processes, but then, for example, you may want to have the one stationary Gaussian process that you want to use. And if you want to pick the one, then usually it will be the one equipped with the heat kernel. Then it comes to the question on what structure do you need to define the canonical heat kernel. And then the structure of homogeneous space may be not enough because it's too soft. So if it's a homogeneous space that happens to be a Riemannian manifold, then it's completely okay. But if it's a topological group which is factorized over a topological subgroup, then you may have problems with defining this V1 kernel. So depending on what you actually want, you can go, you can take one of these paths and get different ways of thinking.
Oh, that sounds very, very interesting. Thanks for the answer. So Sean, do you have a question? I see that you have your microphone turned on.
Yeah, I'm a stupid question, but isn't it the case that these studies, this aspect of geology, the way they are studied, makes it a sub-problem from machine learning? So it's not like bridging completely two different type of studies, but it's to restricting one problem to the other one, no?
You can think about this in this way, yes. So if you consider this story that I told you, like in a few words, it looks like there is the way of approximating posterior Gaussian processes, but it's no clear right away how to sample from these approximate Gaussian processes because they are not straightforwardly amenable to this Matterhorn's trick that just statisticians use. But then it turns out that you actually can make it amenable to Matterhorn's trick by only considering this as a hierarchical model. This is a very simple observation, but it's very useful and it's very since it's so simple, it's very simple to implement and actually use in the applications.
Thank you. I have another stupid question. I'm maybe not so stupid, but one of the problems with Gaussians very often is the fact that it has a very rapid decrease in both directions. While in some natural processes or human processes, in fact, as well, you have fat tails. So if you have fat tails, all the analysis on basis on Gaussian is compromised. So can you be sure that in all the processes that you look at, none of them comes with a fat tail?
Yeah, this is a very good question. So all models are wrong. Some of them are useful. So this is the basic answer to this. It's interesting to study both the Gaussian processes and non-Gaussian processes, of course. The fact that people use so widely Gaussian processes relies maybe not even on the fact that Gaussian is a distribution which arises a lot in the natural world. It comes from the fact that they are easy to handle algorithmically. So you can actually do some computations based on them. And this is why they constitute useful models. Because
but if it's just to permit people to make computations, if the computation have nothing to do with nature or with the human construct you are looking at, what's the point of making computation?
Of course. So you may not need to apply this kind of model to every phenomenon. The problem is that usually when people study the models of different sort, which are non-Gaussian, but people study these models as well. It turns out that the computational burden outweighs everything else, and you cannot use it to solve any problem at all. So this kind of this thing can be used, and you can try, for example, to use it for your data. You can try to learn, does it work well? You can try to analyze, does it fit? And if it doesn't, you can try to do something completely different. And this is what people do. People also try to study other models, but the kind of most prominent problem there is that you cannot actually compute things, and they turn out to be not useful. Yeah.
So following up, Slava, thanks for the talk, and following up on Charles' question, I think I would like to just add a comment. Like, so coming from the industrial perspective and from the geostats community, I would say, like, Charles' point, I think, has a good point. Like, there are let's say restrictions and requirements sometimes from geological modeling or natural phenomena that made the community develop different models that are, for example, exploiting not just the mean and covariance function, but higher order statistics or different types of computational algorithms that allow you to have answers in feasible time. So I'd say, like, just a comment, like a follow-up comment on Charles' point, is that I think Gaussian processes in the industry, for example, in some industries, they have been like put aside, for example, in favor of other models like pluri-Gaussian or multi-point statistical models that not only use the mean function, but also the mean and covariance function, but also other things. So, for example, they can use a reference image to extract statistics that could not be only extracted with 2 points at a time. And so all these things are relevant, I think, to bring into the conversation. Like, there are useful models outside of the useful and tractable models outside of the Gaussian literature.
Yeah, thank you for this comment. Yes, there are, of course, other models, and they may be tractable. Like, my main point was that going out of this class, you have to put a lot of work to make it tractable, and it's very often so hard that you like, for example, if you have a good notion of your problem that can be stated in mathematical terms, you can, for example, get a Bayesian hierarchical model which perfectly fits your assumptions. The very often case is that you cannot do inference with this Bayesian hierarchical model, and you have to do a lot of approximations. And then after this, who knows if this model, if the approximation is actually as good a fit to the circumstances as the original model was. So this is what happens quite often. But of course, yes, in geostatistics, multi-point models, this is something that people use. You can also use other machine learning models like neural networks or something. There is a whole zoo of models out there, and people study different models. So it just so happens that I study Gaussian processes.
Exactly, because I think the point is different objectives, right? So if you feel like someone in industry, for example, geologist or someone that's interested in modeling the natural phenomena, they may sometimes only be interested in sampling something that looks realistic, right? So in order to sample something that looks realistic, you don't need necessarily to have like this treatment as a Gaussian process, but you can do Markov random fields, or you can do training image-based kind of approach, and all the stuff that's not aligned with this objective of trying to do some Bayesian updates on a very well-specified model.
Yeah. And for example, in the Bayesian optimization, you benefit a lot from the model being a Gaussian process, and specifically a Gaussian process, because for many of the very natural acquisition functions, you can compute them in closed form, or for the ones that you cannot compute in closed form, you can get useful approximations by leveraging an approach like the one that I told you about, like conditioning and then sampling and computing some expectations as averages of samples. So yeah, depending on a very specific situation, you will choose your own model, of course.
Thank you, Slava.
Yeah, I would like to comment that Slava managed to give a talk not telling about the main application which was done as a conditioning on slant wells. Yes, might be Slava can slightly comment on this.
Yeah, so the story was that the first time I encountered this problem was actually from the geostatistical perspective, where for some reason the industry wanted to sample posterior Gaussian processes, and there was a lot of data. So it was sparse, but there was a lot of this data, and they also wanted to be gridless. So there is a bunch of approaches based on grids, very classical on how you can do this. But if you want to be gridless, it's a whole other topic. And so it was the problem of modeling some kind of interwell space where the wells had very different shapes, and there was a lot of data along this well. So this is where a lot of data comes from. So this is a problem that we tried to approach. We in the geological application, we ended up doing actually something else because of some of the irrelevant reasons. But we started to dig into the literature, and we found this another view through machine learning and optimization of Kullback-Leibler divergences that helped us build another approach on how you can sample gridlessly with a lot of data. And this is the story. So this is the story of this method.
Thank you, Slava.
I have a remark to make for the group, but that has nothing to do with the talk. Just 1 minute. I did not know that there was in Russia the Chebyshev Center, because that Chebyshev was the name I was going to propose for the postdoc we have with the Pi.
Oh, that's
Center.
yeah. Sergey might take offense at you. I mean, he's
Yeah, no, but it's natural to take. Chebyshev, I think, is a very good choice, but if it's taken already, okay. But then if you go further back in history, there is a name which is very important in terms of somebody doing both theoretical and applied things. It's Archimedes. And Archimedes is also at the origin of the name pi, of the pi number. So I would propose that the doctorate be called after Archimedes.
that's a very interesting idea, actually.
I know that the Slavas, yeah, Slava.
Yeah, I thought you were going to suggest Matheron.
That's a possibility too. So
I thought that you were going to say Markov.
yeah, Right. So, but it seems that now we're, well, perhaps not quite out of questions, but switching over to different subjects. So maybe it's time to thank Slava again for the very nice talk and answering these many questions. And yeah, so let's hope that we have the chance of seeing you in person sometime in the future. Thanks a lot.
Thank you.
Thank you, Slava.